Let us learn about the next property of orthogonal matrices. So if A is an orthogonal matrix, then A inverse is also orthogonal matrix. Okay. So it is given to us that A is orthogonal. We have to prove that A inverse is orthogonal. Okay. This symbol implies A inverse. So we have to prove that A inverse is orthogonal. Now, by the definition of orthogonal matrix, which we have learned three lectures ago. So by the definition of orthogonal matrix, what do we have? We have A transpose is equal to identity matrix, that will be equal to A transpose A. Okay, A transpose is equal to identity matrix, and that is equal to A transpose A. This is from the definition of orthogonal matrices. This expression, which has been marked as equation 1, this equation 1 came from where? It came from the definition of orthogonal matrices. So this expression came from the definition of orthogonal matrices. Now let us take inverse on all the sides. So this entity's inverse can be written like this: A transpose inverse. Identity matrix inverse can be written like this. Okay, and A transpose A inverse can be written like this. Okay, this equality will hold good if we take transpose on all the sides, on all the three sides. Okay, so this equality will still hold good. If you take inverse of this equation 1, it will still hold good. So inverse will still hold good. Okay, so we have written that. Now we know this property that AB inverse is equal to B inverse A inverse. AB complete inverse is equal to B inverse A inverse. So this is A, this is B. Okay, so AB complete inverse. So A transpose inverse will come in the front. Okay, A transpose inverse will come in the front, and this A will become the second term and transpose will come over there. So A transpose inverse, A inverse. Okay, then second term I inverse. Identity matrix inverse is equal to identity matrix itself. So that will be equal to identity matrix itself. Okay, and A transpose A, we know this property, right? I am writing the property once again so that it is clear to you. Okay, AB inverse is equal to what? It is equal to B inverse A inverse. Now apply this property on this particular term. Apply this property on this. What will it come out to be? It will come out to be A inverse multiplied by A transpose inverse, right? It will become like this. So let us check. So it is A inverse A transpose inverse. Okay, as I have written A inverse A transpose inverse, in a similar fashion it is written A inverse A transpose inverse. Okay, this is the thing. So this is what we got from here by using this property, by applying this particular property where? By applying that particular property over here. The property has been written once again over here. This property we have applied on this expression, Okay, so we have successfully applied that. So after applying that property, we get this kind of expression. This kind of expression is the thing which we get. Now we already know this particular property that A inverses transpose. If you take inverse first and then take transpose, it is equal to taking transpose first and then taking inverse. Okay, what is the difference in this expression? What is the difference? The difference is that over here you are taking inverse first and then transpose, and over here you are taking transpose first and then inverse. Okay, inverse first then transpose first then inverse. Okay, this is the difference. So A transpose inverse can be written as A inverse transpose. A transpose inverse can be written as A inverse transpose by using this property. Okay, this transpose can go here, inverse can come here. This transpose can go here, inverse can come here. Okay, so it has been successfully written like this. Now apply the definition of orthogonal matrices. If A inverse is orthogonal, this expression will hold good. If A inverse is orthogonal, if A inverse matrix is orthogonal, this will hold good. So this is holding good. So A inverse is orthogonal. This statement implies that A inverse is orthogonal. Okay, this particular expression implies that A inverse is orthogonal. Okay, how does it imply? This implies from the definition. of orthogonal matrix. Okay, so this expression is implying that A inverse is orthogonal. And how is it implying? From the definition of orthogonal matrices. So A inverse is orthogonal. But we had started with the fact that A is orthogonal. We had started with the fact that A is orthogonal matrix. We started with that, and we have reached that A inverse is orthogonal. We started with A is orthogonal, and we reached that A inverse is orthogonal. Okay, so inverse of an orthogonal matrix is also orthogonal. That is the meaning. Okay, so A is orthogonal and we are taking its inverse, so its inverse is also coming out to be orthogonal. So inverse of an orthogonal matrix is also orthogonal. Okay, once again I am reading the statement: inverse of an orthogonal matrix is also an orthogonal matrix. Okay.